Welcome. We will be discussing the shattering curse of dimensionality. We're going to explore exactly how deep learning and stochastic paths have finally solved the mathematical bottleneck in high dimensional PDEs. So, for decades, the universal language of mathematics has been trapped in a metaphorical cage. In 1957, Bellman coined the phrase the curse of dimensionality while working on dynamic programming. This curse governs systems across a multitude of disciplines, from the Schrödinger equation for quantum many-body problems in physics to the Black-Scholes equation for pricing derivatives in finance, and even Bellman equations in control theory. In all of these fields, the dimensions of the equations scale up rapidly as we add more particles, underlying assets, or autonomous agents. So, let's visualize the geometry of this curse. If we start in a simple one-dimensional line and want to distinguish 10 regions, we just need 10 distinct cells. Moving to a 2D square with that exact same resolution requires 10 by 10, so 100 cells. So by step 3, a 3D cube exceeds 1000 cells. The diagnostic rule here is that for d dimensions and v values per axis, classical solvers require ov to the power of d regions. The complexity grows exponentially, demanding an impossible number of computational nodes. This brings us to the 100-dimensional wall, which illustrates the math of impossibility. To evaluate a relatively simple 10-stage process on a coarse grid, we need 10 to the power of 10 points, assuming a computational speed of 1 point per microsecond. Calculating those points would take almost 3 hours. But if we scale that to a 20-stage process, we hit 10 to the power of 20 points, which would take millennia to compute at the same speed. So in a real-world context, modeling a modern financial portfolio with a standard Black-Scholes equation frequently requires calculating 100 simultaneous assets. This 100-dimensional space creates an OV to the times of 100 computation, which is physical impossibility for grid-based models. There is another fundamental issue, which is the emptiness of high-dimensional space, which creates a statistical trap. Classical grid methods relied on local generalization, meaning they estimate the value of an unknown point by looking at nearby training examples within the same grid cell. But in 100 dimensions, the number of possible configurations is very vast, meaning almost every single grid cell is completely empty. You simply cannot learn locally when there are no local neighbors. As a result, the grid framework fundamentally breaks down in high dimensions. So, to move forward, we must abandon the grid entirely. To escape this exponential curse of dimensionality, we have to stop trying to mesh the universe. Instead, we must learn to approximate the mathematical function directly. So this is where the neural networks offer a solution through distributed representation. Think of it as a cube tray. It rigidly cuts space into mutually exclusive boxes and require a separate set of parameters for every single region. Neural networks, on the other hand, act like an origami. They use distributed intersecting half planes or activation functions to divide the space. Mathematically, a network with n features in a d dimensions can assign a unique codes to on to the power of d distinct regions using only on by n parameters. This provides our mathematical escape, achieving exponential distinction using only polynomial parameters. Furthermore, deep learning relies on composition over addition. Classical approximation theories build functions additively, typically by summing polynomials or wavelets, making them highly vulnerable to dimensional scaling. Deep learning universal approximation builds functions compositionally instead. So a multi-layer network learns the global shape of a target function directly from sampled points, completely bypassing the need to compute the function everywhere on a fixed mesh. But how do we connect these two different words? Neural networks are powerful function approximators, but continuous physical and financial systems over time are governed by parabolic PDEs. The missing link here is the BSD formulation. So in a 2018 breakthrough, researchers demonstrated that general high-dimensional parabolic PDEs can be reformulated using the BSD equation. This brilliantly frames the continuous equation as a deep learning problem. This formulation allows us to rewrite space as stochastic paths. So instead of calculating an entire spatial grid at every single time step, we simulate forward paths, specifically Brownian motion trajectories flowing through time. To conceptualize this shift, imagine dropping a fleet of smart sensors into fluid to trace the current, rather than trying to build massive rigid cage to measure the entire ocean. So we can understand this mechanism through reinforcement learning analogy. The forward stochastic path, Brownian motion, acts our simulated environment. The unknown spatial gradient of the PDE solution acts as our policy function, which determines the system's trajectory. This gradient is exactly what the neural network learns to approximate. Finally, the loss function acts as our reward or penalty derived from the difference between the neural network output and the explicitly known terminal condition of the PDE at time t. So, here's how the BSD architecture executes this in a loop. Starting by step 1, discretize the time interval into segments, and then sample stochastic forward paths via the Brownian motion, and then use the deep neural network to approximate the spatial gradient at each step. And the step 4 is to step the solution forward in time using the network's gradient output. Then compute the expected loss against our known terminal condition and backpropagate to update the network's weights. To synthesize these two paradigms, classical PDE solvers use a rigid, mutually exclusive mesh-based representation, while the deep BSD method relies on a mesh-free distributed representation using intersecting half planes. Classical computational scaling is exponential, but the deep BSD achieves polynomial scaling. Evaluation shifts from global grids to sampled stochastic paths, and the nature of the mathematical solution moves from additive polynomials to compositional multi-layer activation. Now let's look at the real world results of shattering that 100-dimensional wall in the black controls. The problem was pricing financial derivatives based on 100 underlying assets simultaneously while factoring the in nonlinear default risk, a task where classical grids fail instantly. So the result is that the model converged in just 1600 seconds running on a standard MacBook Pro, yielding a relative error of only 0.64%. The impact is significant. It allows analysts to rigorously incorporate default risks into the 100-dimensional pricing models, helping prevent the systemic modeling failures we've seen in past credit crises. This same approach is dramatically expanding in the frontier in control theory and physics as well. When applied to the 100-dimensional Hamilton-Jacobi-Bellman equation for dynamic programming and multi-agent game theory, the model reached 0.17% relative error in just 330 seconds. And for the 100-dimensional Allen-Khan equation used in reaction diffusion, phase separation, and quantum prototypes, it achieved a 0.3% relative error in 674 seconds. So, to conclude, the future of high-dimensional mathematics relies on abandoning the grid by bridging neural network approximations with stochastic paths. We bypass the exponential trap of the 20th century. This breakthrough unlocks real-time multi-agent game theory, total system resource allocation, and highly complex financial modeling. So, as a final thought, we no longer need to mesh the universe to understand it. We can simply trace its paths.